Okay, our next speaker is Per Stritzinger. Did I do it? Good job. Insight from Grid Platforms. Take it away.
Okay. Yeah, it's great to be here again. I was at the Flight Software Workshop last year for my first visit, and now I'm speaking, so this turned out quite nicely. Today, I'm trying to get you familiarized with some maybe alien concepts to you in programming languages. It will be a hard sell, I know, because we are all kind of like set on the ways we are actually working. And also there's this blob paradox, which is basically if you work in a higher level language, then you can see clearly which features are missing in lower level languages. But if you actually look upwards the ladder in higher level languages, you think there are kind of like very weird and unnecessary features in the higher level languages, which is kind of like a paradox, because as soon as you get there, it's like, yeah, how could I work without those? And so this paradox was formulated by Paul Graham, and he was talking about Lisp in the very good article that is linked underneath here. And I would say, having done quite a bit of Lisp in my career, that Erlang, the programming language I want to actually talk to you about today, is even above Lisp, because it has everything Lisp has and more. Yeah. So
let me try to sell you this. Got echo? Yeah.
Yeah, because his he wanted the camera for his different.
But the audio is not on. Yeah.
Yes? Ah, no, it's gone. For some reason, the microphone switched itself on. Didn't do anything. It wasn't me. So what do we get in Erlang basically? I have to run this very quick because there's so many features in there. But I will then focus on one, which is the unique selling point. Now, one thing is we get transparent distributed programming.
I did that.
That means that basically, if you talk to a process on another node computer, basically it's transparent. You don't know if it's the same node or another node, except latency, of course. You can't do anything about late speed. The main feature, the main unique selling point is failure tolerance, and that's actually why I'm talking to you about that here, because that's obviously a very useful feature if you have hardware you can't get to anymore very easily. It would be actually nice if it could repair itself. And I will get you a lot of details about that later on. It's also soft real-time, which is also useful for all kinds of embedded systems work, because very often we don't need hard real-time for lots of tasks, but soft real-time would be a good thing. So we don't want long pauses, let's say Java, stop the world, garbage collection, holding up everything forever. Kind of like as a side effect, you get insane level of concurrency. It's kind of like what Erlang hyped in around 2010, because nobody knew what to do with multi-core computers and really make use of them. But Erlang just worked. You got a 128-core CPU and could actually, if you wrote your program the normal way you're supposed to do it, with lots of processes, it used the whole CPU. But we took care of that because we now have microservices. But unfortunately, they are pretty wasteful. A little bit on that maybe later too. Because it's a functional language, it gives you higher productivity and lower time to market. It has a lot of like little features which are not very obvious, which speed up development quite a lot. So what else do we get? It's a safe functional language. It has actual optional type checking. It's a dynamic language, but it has strict dynamic types. So it's not like, let's say, JavaScript, where kind of like a string magically turns into a number and vice versa. But a type stays a type. but it's a dynamic type. So not always can you statically type check at compile time, but in many cases you can, and we actually have 5 different type checkers. So we have pluggable type systems and a lot of type checkers, and getting more recently. It has immutable data, so every data is never modified, so it's always copied. Sounds wasteful at the beginning, but actually doesn't turn out to be. It has a share nothing data model. So Erlang has lots of processes, and these are like not threads, they're operating system processes. Except they're not operating system processes, but they are much more lightweight. But they behave like operating system processes, so they each have their own memory, and also kind of like we heard recently in the last talk, second to last talk, this would give you space partitioning. So one process can't touch the memory of another process. Running a little bit ahead, these processes are very lightweight. That gives you this insane concurrency. A process on a 32-bit machine takes about 300 bytes of memory. And you can have easily on a laptop 10 billion processes, and it would just work. Sounds unbelievable, but it actually works that way. That's why WhatsApp is built in Erlang, and that's why it works so well. You have asynchronous message passing between these processes, which is basically the only way they can communicate. They can send messages to each other, and that's all. They can't touch the memory or anything of the other process. The processes can also be linked or monitored. So linking is if you tie together 2 processes, if one of them crashes, it takes the other with it, basically. They both crash. Unless one of them kind of like says, okay, I want to trap this and do something about the other crashing process. It's in the supervisor case. Monitoring is a different thing. It's a one-way thing. It's not tying together, but I can message when another. So we can actually watch other processes. It's a garbage collected language, so no memory, no manual memory allocation and stuff like that. And the interesting feature is, which they got right in Erlang, is they have garbage collection per this lightweight process. So if you do this in a lightweight process, you don't get the stop the world garbage collection because you have only little heaps that get garbage collected. So A, that's over quick, and B, it doesn't stop the world because all the other processes can do some work while one process is garbage collecting. And very often they never garbage collect because worker processes are often spawned, very lightweight, also very quick, nanoseconds, and do their work and then disappear without ever having to be garbage collected. There's a big library. It's called Open Telephony Platform because that's where Erlang comes from. It comes from Telcom. But it's actually their standard library, which has a lot of abstractions. And around these processes also, it has behaviors, which lets you kind of like do the gnarly part of, let's say, handling processes in a standard library part. And you only have to write callback functions that get called by this handling part, which are then pure functional again. So no side effects necessary there in your code. So your code gets much easier to understand. It's also kind of like an operating system because it has everything that operating systems has. So it's a little operating system within the operating system, and we will make use of that by getting rid of the operating system, kind of. But we get to that. Yeah, I'll run through quick. It's still maintained by Ericsson, the telco company. They still use it for their 5G products. They have millions of lines of Erlang code, so they will always maintain it, I guess, as long as they're in business. And so the last 30 years, basically 15 people have been improving the VM, and so we are benefiting from continuous improvements, but they're also because the telco industry, they care also about similar things. They have a responsible release engineering, so no quick deprecation of things. Every features are not getting added very fast. It's actually pretty pleasant to work with, even if you have products which are 10 years out working in an embedded system, for example. There's also the Erlang Ecosystem Foundation. I'm rushing over that. So there's a user organization that takes care of the things. But let's get to failure tolerance. So probably lots of you have called tech support and they told you to switch your computer off and on again. And of course you're annoyed by that because it's kind of like, why can't they fix this other ways? But surprisingly often it just works. You switch it off, you switch it on, and the problem is gone. So why is that? Or how can you actually make use of that? In Erlang, we say let it crash, which gets often misunderstood by management because it doesn't sound positive. But the whole idea behind let it crash is that if you have corrupt state in your program, which is always if you have a bug, you get corrupt state, your state is corrupted. You kind of like need to get rid of the corrupt state. And the learning is you cannot fix corrupt state from within the corrupt state. But you have to do it from outside, basically. Because the corrupt state, you can't predict how it's corrupt, so you can't fix it from inside, so you do it from outside. And the only way to do it from outside is to get rid of the corrupt state as fast as possible, so you let the process crash and the state gets corrupt as fast as possible. And the process from outside, that's another process, that's a supervisor that watches other processes, basically, mostly all of your processes, then restarts the process. And we will actually look at research why this works so well. So let's first look at a very simple supervisor. So the blue box is a supervisor, so one process, and the green boxes are child processes that the supervisor watches. And this is a one-for-one supervisor. That's one type of supervisor that basically is for like one child crashes. One child crashes, and the supervisor gets notified, and it just restarts this one child. Very simple. But sometimes you have lots of processes communicate very intensively within each other, so the corrupt state very likely escaped this one process by message passing, by sending a corrupt message. And then you need an all-for-one supervisor. So when one process crashes, the supervisor kills all the other processes and restarts all of them. And it kills them in the reverse order, it starts them, by the way. And there's also like another one, a rest for one supervisor. Let's assume these, the green processes are kind of like a pipeline from left to right. So if this one crashes, the left one cannot be affected. So it only needs to restart the right processes. So that sounds very simple. So does this even work? Well, it kind of works like microservices copy that. If your microservice crashes, Kubernetes starts it again. So that part is known. But we do this at a much more fine-grained granularity. And we not only have one supervisor, but we have a tree of supervisors. So you organize all your processes in your system into a tree of supervisors. And every supervisor can be a different type and can be configured differently. And there's also a maximum restart frequency. So if the processes of one supervisor, and this one process, kind of like crash more often than you configured, like in this time 3 times in, let's say, a minute, then the supervisor itself kills itself. By this kills all the children, and the whole subtree gets restarted. And by this, you kind of like have an adaptive way of restarting very, very small parts first and then getting wider and wider and wider. So why does this work? There is some research from 1985 from Tandem Computer, who already figured out back then that you need 2 computers or 2 cores to actually be fault tolerant, because one computer can die. We all know that. And they researched why do computers in programs fail in production, and kind of like sorted the bugs in different bugs, which they called war bugs and Heisen bugs, like transient bugs and repeatable bugs. And if you look at testing or in production, you can find the repeatable bugs usually very easily, except maybe in secondary features, you didn't write the test for that. Sometimes overlooked, but transient bugs are very hard to find. Often the system needs to run a long time, and only then it crashes. But if you look at what happens when you restart, then especially these transient bugs are very easy to fix with restarting, because the corrupt state will not get corrupt very quickly again. So you restart it, you log it, you look at it later, and fix the problem at your leisure. And the system has fixed itself. And interestingly, these transient bugs are actually the majority of these bugs from this research from 1985. We all know about hardware watchdogs. That's basically the way how we restart a whole system if it kind of like doesn't react anymore. And we can also tie into that. And with the Erlang supervisors, we have a much more fine-grained control about what we want to restart, like really small parts of the system. Yeah, that's more to read, like how you design your system. So how to design a supervisor tree, that's actually the hard part to learn, to really build fault-tolerant softwares. To rush a bit forward. So Ericsson actually achieved with an ATM switch, achieved 9 nines availability. That includes software updates, by the way. So that's 32 milliseconds per year not available. In telco, with 5 nines you're in business. And 9 nines was very unbelievable, but it was actually measured by the customer, which was BT in their ATM network. So this is the 9 nines that Erlang is famous for. Of course, this doesn't happen by itself. You need to do a lot of work on your own side, but it gives you all the tools to achieve a system that is as reliable. Very short overview. You have these supervisor trees, so the little blue trees, and these are grouped into Erlang applications, which are then grouped into an Erlang release. So an Erlang application is kind of like a library with some executable state with a supervisor tree, usually. And you can start and stop them manually or automatically. And they are also kind of like then one unit of a library that you can install into a system or bundle into a release. So kind of like to go with the microservice thing, when we look at an Erlang process, let's call this process a picoservice. And so yeah, we know that already. An application would be a nanoservice then. And the whole thing would be a microservice, the whole Erlang node, basically, which could collaborate with other microservices and be managed by the usual Kubernetes, Docker, and you name it, things. So if you look at that, between microservices, you have milliseconds latency. That's one of the problems that you have when you have lots of microservices. But anything within an Erlang VM has nanosecond latency. And that's also a big difference. So it's much more performant while giving you the same properties as microservices at a more fine-grained level. So let's get to the demo. I hope everything works. So on this demo, I actually have a board here. I need to change my screen sharing to whole screen. Yeah. And then let's make this slide smaller. So here you see a board. I will quickly tell you about this board later on. And on the board, you see 2 blinking lights. One is blinking regularly in green. That's the left one. That is managed by this green blink process, which blinks in green on the left LED very regularly. And then there's another supervisor, which is a sub-supervisor of the one supervisor. And it actually has a bunch of processes. One is called Sybil, which is kind of like not doing anything, except when we start the process, whenever it gets started, it sends a message called next color to the green blink, which lets it blink in another color. Kind of like that, and the name is not correct anymore. That's kind of like to watch whenever this supervisor crashes, then we see the blink color of the left one change. The right one, the right LED, is kind of like irregularly blinking. That's because it's kind of like controlled by these red, green, and blue versions of the basal processes, which override each other, one in each color, which has kind of like a random pattern of blinking. And let's look at this random pattern in the code and then introduce a little bug in there. Because currently it's working nicely. It's blinking since hours. It blinked last day, all day. So that's actually what how Erlang code looks like. So sorry about that. It has Prolog-like syntax. It's kind of like the thing that I left away that is getting used to. But people complain about the syntax all the time, but now they make Rust. I don't know. Get it? Probably the same people. So what we do here is basically we get timeout messages regularly, and we want to specify the interval. And because we want a certain statistics, we kind of like have 20,000 milliseconds divided by a random interval that we calculate. And they calculated in, so we have the old interval, and we multiply by a random number from 1 to 100, and take the remainder of 100, add 1, and that is the next interval that we actually get. The add 1 is very important because that kind of like prevents that this whole thing gets 0. So let's remove it. And I compile this module, and I promise we can do hot code loading. That actually hot code loads the code into this node. And now we should see crashes. And it doesn't crash. That's weird. Oh, I didn't save. Okay, let's compile again. First crash. I'll show the blink again. So you see the left one blinks green quite nicely, and the right one kind of like keeps crashing and blinks irregularly and keeps crashing and crashing and crashing. But the important green one kind of like keeps blinking on and doesn't change its color because it's configured correctly. But what if we actually make another little change? And we reduce this 20,000 milliseconds to 5,000 milliseconds. So the crashing happens much more often now, which should actually let the supervisor itself crash. And when the supervisor crashes and restarts the whole children, the civil process also gets crashed, and the color, there we are. Oh, I'm sorry, I didn't show you the video. The color changed, the color keeps changing. So that's when the whole supervisor crashes and the other one gets started. Okay. I'm running out of time. I have too many slides, of course. But maybe let me rush quickly through the slides. I need to find my slide window again. Okay. So this whole board actually runs the Erlang VM directly on hardware. We combined it with RTEMS, which many of you might know, which allows us to put it in very small hardware.
And also, which kind of like...
So if I hit the key, the microphone switches on. Yeah, I don't need to explain you that. So, and with this RTEMS thing, you can actually build mixed critical systems. So you can have your critical flight software in your existing C code because you don't trust this new Erlang thing yet. And run the Erlang software real-time stuff, high-level functionalities, or your experiments with its space partitioning at a lower priority, and by that get a mixed critical system that is allowing you to actually maybe have a new way of running systems. So I need to wrap it up, I think. Yeah, you can also mix up the priorities differently. Network stack in the middle. So that's the hardware. That's the smallest hardware we want to run. The rest you can read up in the slides, and that's the end.
I don't see any questions online. There's one in person. We can take one question, maybe two at most.
Hi, I'm just curious. I don't know much about Erlang, so this might sound like a silly question. How deterministic is the garbage collection in this language? Because it sounds like there's some sort of VM running, it's a high-level language. Yep. You know, in languages like C++ and Rust, hopefully I don't get in trouble for saying this, but you essentially have a deterministic garbage collection, right? You know when things are getting cleaned up. What's the story here with garbage collections, what I'm asking? How deterministic is it?
So Erlang has a runtime, like a virtual machine. It initially ran some like a bytecode into there, actually threaded code like Force. But nowadays we have just-in-time compilation. So it actually, every module gets just-in-time compiled when it's loaded. And this is one of the ongoing optimizations that makes everything faster and faster. And the important thing is that the garbage collection works per this little process. So it's a copying garbage collector that have like a generational garbage collector that works per process. And since the process often has only like 1,000 bytes or 2,000 bytes of heap, it's very quickly garbage collected and not very disruptive, and therefore it can actually work as soft real time quite well.
Just to be clear, this system of the hierarchical supervisors, which can delete themselves or delete their children, is this something that is just part of Erlang, or is it something that Erlang gives you the tools to do?
So the base language gives you the tools like linking, processes, etc., and the supervisors are part of OTP, of the library.
Okay, thank you.
Which also do the hot code upgrade of whole systems, because the supervisor tree is also the orchestration, how hot code upgrades work.
Okay, there's one online question. Is it feasible to transition to Elixir while retaining all of the advantages while leveraging the modern features and capabilities offered by Elixir?
So yeah, Elixir is another language that's running on the same VM. It actually compiles to Erlang. So it's kind of like a difference. And it actually started as that Ruby people wanted to have Ruby flavored Erlang. That's basically Elixir. It's an Erlang with Ruby syntax, and it's not more modern. It is just different. It hasn't anything more. It has more for web development basically. So if you want to write a quick website, Elixir is your place to go, especially if you want to use existing web developers. Otherwise, both are kind of like at the same power level. So I wouldn't say old or new. I mean, yeah, Erlang is old, but it also gives you more control and it gives you a better understanding of what's actually happening underneath.
Thank you. There are a couple more questions. Please follow up with them through Slack channel. Thank you so much.